Hello. So today I'm going to be going over some practice problems that will help prepare you for your third exam. So exam 3 is going to cover chapter 7, which goes through your substitution and elimination type reactions. These reactions are really important because the substitution and elimination processes occur in many of the common name type reactions that you'll learn towards the end of this semester and then all through second semester organic chemistry. So substitution and elimination reactions are very important and occur in many other as part of many other mechanisms that you'll see throughout this semester and next semester. So the first type of substitution reaction is your SN2. So SN2 is a concerted process in which you have a nucleophile doing a backside attack on your substrate here. Typically, it's going to be a primary or methyl substrate, but you could also have a secondary, which you have here in this case. So it's a concerted process, meaning that you have your nucleophile coming in, and in a single step, you will have a loss of leaving group, which is a bromine in this case, and you'll form a new product that displays an inversion of stereochemistry. So you went from an R to an S configuration. Now, the reason why these reactions will typically occur on primary and methyl substrates, and in some cases on secondary substrates, is because of steric interactions. That's kind of one way to look at it. And so if you look at the transition state here, you have your nucleophile. You have a species that contains both the incoming nucleophile and your leaving group. And so when you have substrates that are very bulky, like a tertiary substrate, this transition state here, or formation of this transition state, is just not going to occur as readily. And so that's why SN2 reactions are typically not going to be as reactive when you're using a tertiary substrate. Now, you also have your SN1 reactions. These are stepwise process where you have a loss of leaving group, typically a halogen or the conjugate base of a strong acid, forming a carbocation. In this case, you have a tertiary carbocation, which is highly stabilized, and that then leaves a very strong electrophilic center for a nucleophile to come in and do a nucleophilic attack, which will then produce your final product. So the rate of these SN1 reactions is just dependent on the substrate. And also something to note is that these SN1 and also E1 reactions typically require a polar protic solvent system because of, let's say we're using something like ethanol. Well, you see here, you're forming this leaving group. So now you have a negatively charged anion in your solution. And what happens is when you're using a polar protic solvent, you have this induction that occurs within the solvent because of the difference in electronegativity between oxygen and hydrogen. So you have this slight delta positive on the hydrogen and a slight delta negative on the oxygen, which allows for hydrogen bonding to occur between the leaving group and your solvent. So that's why a polar protic solvent is typically going to be used in your SN1 and E1 reactions, where you're going to generate a leaving group that can be more stabilized. So the exam is also going to cover your elimination type reactions. You have, again, a concerted elimination reaction called the E2 reaction, where you have a base come in and deprotonate your beta carbon here, or a hydrogen off of your beta proton, I guess they would call it. And then you have a loss of leaving group of your halogen forming a double bond. This is going to be synthetically very useful when you guys go into chapter 8, or addition reactions of alkenes. When you want to generate an alkene, you'll do a radical bromination followed by an elimination, typically an E2 elimination, leaving your you with your alkene product that you could then undergo different addition of alkene reactions. You also have an E1 mechanism here. This is a stepwise process where, again, you have your loss of leaving group. You then have a base come in, deprotonate, forming your alkene product here. Okay, so it's also important, as I mentioned, to keep in mind the solvent effects that occur in your reactions. And so you see the chart here, we've got some different common polar protic solvents that can all contain a hydrogen connected to an electronegative species. And these are going to be used mostly in your E1 and SN1 reactions. You also have polar aprotic solvents. These ones do not contain a proton connected to an electronegative species. These will be used in your SN2 and E2 reactions. So there is a significant correlation between solvent and the rate of reaction, which is shown in these charts down here. So maybe glance over these to help review for that. This slide kind of covers an overview of some of the different reactions that are covered in this chapter, and it kind of guides you through the reactions from a reagent perspective. So understanding that if you have a primary alkyl halide, in this case, depending on what reagent you react it with, you can afford varying different final products. So ideally, what you should be able to do is take a substrate like a primary alkyl halide, like in this case here, and you should be able to kind of work backwards. If you're given a final product of a nitrile, like in this case, you should be able to figure out that in order to achieve that final product, you'll need to add sodium cyanide to the solution in order to get that product. On the bottom here, this kind of just goes over some of your elimination type reactions and varying reactions that will occur on a tertiary substrate. That's kind of a nice little overview. So how do you approach working through substitution and elimination type reactions? Well, the book kind of goes over a very systematic approach to doing this. First, what you want to do is analyze your substrate and classify it as primary, secondary, or tertiary. And then you want to look at your reagent. And the chart over here shows you some of the common reagents, and it allows you to see whether they're strong bases and weak nucleophiles. In the case of DBN and DBU, these are very bulky bases, so they can't function as nucleophiles, but they are excellent bases when you're trying to do elimination type reactions. And then the really common ones here are going to be your strong base, strong nucleophile, weak base, strong nucleophile, weak base, weak nucleophile. So it's important to kind of try to memorize some of these if you can, because they will definitely come up on the exam and in subsequent chapters. So next, once you figure out what type of substrate you have and what type of reagent you have, you can use this chart that's shown in the back of the textbook to kind of determine which type of product is going to be formed in the majority. So essentially the way this works is you'll say, let's say you have a primary substrate and you have a strong base. weak nucleophile, you know that your product is going to be mostly, and in this case, entirely that E2 product. So this chart can be kind of handy. First, figure out what type of substrate you have. Next, classify your reagent, and then use this chart to help kind of guide you through determining what type of product is going to be produced. Lastly, there's some regio and stereochemical factors that you have to keep in mind in determining what the majority product is going to be. In this case, you have a secondary alkyl halide treated with sodium ethoxide. So again, if you look at this chart over here, secondary sodium ethoxide is a strong base and strong nucleophile. The majority product is going to be your E2 product, which is shown here. The reason why the majority product is in the trans configuration versus the cis configuration is because of the steric interactions that occur in the cis configuration. There's more steric interactions, I should say, and that should be kind of a review from previous chapters that you guys have studied. And also, you will get some SN2 product. One of the kind of big things that should stick out to you is the inversion of stereochemistry. So you know that there was an SN2 process that occurred between the starting material and to afford your final product there. And then also you get some of this minor Hoffman product, which is again going to be a minor product because it's mono-substituted. So your product here, the major product, is di-substituted and it's trans. This guy is minor because it's di-substituted, but it's cis. So the cis configuration is going to have more steric interactions. This guy is going to be another minor product because it's mono-substituted, less stable than the di-substituted. So these are it kind of gives you a good overview of what to expect when you're doing these generic substitution elimination type reactions. It's important to understand all of the products that can be produced. And then you can use your solvent and temperatures and things like that to try and make your synthesis a little bit more efficient to produce mostly one product over the other. But in this case, it's important to just kind of be able to determine all of the products that could occur. And one of the more complicated problems that you'll see, I think, is going to be your E2, type reactions, because there is some kind of tricky regiochemistry that occurs. So also keep in mind when you're looking at a problem that is going to go through an E2 pathway, you first want to identify your beta protons, which has been done in this over here. So you identify your beta protons, and then you can determine what products will be produced. In this case, these guys 1 and 2 are actually identical, but you also could get this product down here, which is going to be your Hoffman product, your less substituted product. And that would be produced if a bulky base was used versus a non-sterically hindered base. So in some cases, synthetically, you will want to produce this Hoffman product in order to kind of have a good starting material to undergo other addition type reactions. And so it might be important to produce a Hoffman product versus your Zaitsev product for synthetic purposes. And this chart down here gives you a nice overview of that topic. So let's go through some practice problems. The following mechanisms depict two potential methods for synthesizing the same ether, but only one of them is possible. Explain. So first, you want to take a look at your substrate. We have a tertiary substrate in this case. And let's look at our reagents. We have sodium methoxide, which is a strong base, strong nucleophile. So in this case, if you treat this tertiary substrate with sodium methoxide, instead of getting your desired product, ether product, you are actually going to get an elimination product. So you identify your beta proton. In this case, all of the protons are going to be equal, so it doesn't matter which one you choose, but you have your base come in. I guess I should draw this in a little bit different. Producing your elimination product. So the first mechanism here is not going to produce the desired product. So clearly the second one hopefully will. So in this case, we have a methyl iodide substrate. Reacting with sodium tert butoxide. So again, you have a methyl in this case reacting with a strong base, strong nucleophile. This will produce predominantly your SN2 product, which is the desired product in this case. So you have this guy coming in, doing a backside attack, followed by loss of leaving group. And this is actually kind of the majority of name reaction known as a Williamson ether synthesis. That you will learn next semester in chapter 13 a little bit more. But this kind of illustrates what I was mentioning before, and the fact that a lot of these SN2 processes occur in many important and synthetically useful reactions that you'll learn as you progress on through organic chemistry. Okay, next question. Identify the reagents required to achieve the following transformations. So for A, you have OTS here. This is a tosylate. So essentially, this is going to be an excellent leaving group. When you have a really poor leaving group, you can treat it, you can do a reaction with tosyl chloride and pyridine to form your tosylated product. And this can then undergo an SN2 type reaction to produce your desired product. And so in this case, this is going to be an SN2 reaction, and we're going to want sodium hydroxide. Okay, let's look at B. So in this case, we have an alcohol as our leaving group, which, as we know, is a very, very poor leaving group. So what we first need to do is tosylate this in order to produce a really good leaving group, and then do an SN2 type reaction to produce our final product. So what we'll do is we'll add tosyl chloride, pyridine, which will produce something like that. And then we can treat this with sodium cyanide to produce our nitrile product. Sodium cyanide is something that you guys were mentioning when I was going through the review session. This is a really common reagent that's used for SN2 processes. It's used in the and reactions of carboxylic acids to produce carboxylic acid. So this is something that you will see commonly. If you haven't seen it yet, it's something that you might want to write down. Okay, for C, again, we have a tertiary alcohol and we're going to form an alkyl halide product. So this is going to be an SN1 reaction. And in this case, we can actually just use HBr. The reason why is because we have a tertiary substrate, so we can produce a stabilized carbocation, tertiary carbocation, that would then undergo an nucleophilic attack by the bromine. So let me draw that out real quick for you. All right. D. First thing that stands out to me with this problem is the inversion of stereochemistry. So obviously that should be just screaming out to you that an SN2 process has occurred. So in this case, we know we just need a really strong nucleophile, and we can use, sodium, this guy here. Okay. Identify the major and minor products of the following reactions. All right, so in this case, we have a secondary substrate, and we're treating it with tert butoxide. This is a strong base, strong nucleophile, but it's also a very bulky, sterically hindered base. So we look at our chart down here. We've got a secondary, we've got a strong base, strong nucleophile. We're going to produce mostly the E2 product. And in this case, majority product is going to be our Hoffman product because of the base that's used. If we had used something like sodium hydroxide, which we'll do in C, you're not going to get the Hoffman elimination product as your majority. Okay, and also just to draw out, you'll get some minor products as well. Okay, for B, you have a primary substrate and you're using strong base, strong nucleophile. So you look at the chart here, strong base, strong nucleophile, primary substrate, SN2 reaction is going to occur predominantly. So major product is going to be butanol. But we're also going to get some E2 product. Oops. Sorry about that. We'll also get some E2 product. Oops, I'm sorry. I can't. It would just be this is your E2 product. You look at the beta protons there. Okay. For part C, again, you have a secondary substrate, and in this case, we have a strong base, strong nucleophile, but it's non-sterically hindered. So in this case, we are going to also do an elimination reaction like in part A, but our major product is going to be the Zaitsev, simply because of the hindrance of the base, so it's less sterically hindered than the tert butoxide that was used in part A. So this guy's going to be your primary. or your majority product, but you also get some SN2 product, and you also get some Hoffman product. Okay, for part D, see here, we got sodium ethoxide, so strong base, strong nucleophile again, and we got a tertiary substrate in this case. So according to the chart down here, the E2 product is going to be our sole product. So let's first look for our beta protons. So we're going to have two different products formed. And in this case, our more substituted alkene product is going to be the majority product, which is this guy here. Okay, this is kind of a tricky one. Identify the major and minor products of the following reactions. So in this case, we've got a secondary substrate, and we've got a strong base, strong nucleophile, but also notice that we've got reaction occurring in ethanol solvent. So that's a polar protic solvent. So that's going to favor your elimination product. So in this case, you're going to produce primarily an elimination product. So we're looking at elimination reactions. First thing you want to do is identify your beta protons. In this case, we notice we just have one beta proton. Now, what is the important thing to keep in mind about E2 reactions? Well, it's the fact that E2 reactions tend to be very stereospecific, or I should say stereoselective. So essentially, you need to have your leaving group and your proton being abstracted in the same plane. So essentially, you want these guys to be anti-periplanar. I guess that would be the proper term. So what we need to do in order to figure out what product we're going to get is figure out what that anti-periplanar configuration is going to look like. And there's a couple ways to do it. First thing I'm going to do is show you guys with the Newman projection. So we've got, if we're looking from this direction here, you got your bromine, you've got your phenyl, and you've got a proton. And in this case here, we've got our proton here, ethyl group, and then methyl group. Okay, so what we want to do is get our proton and leaving group in an anti-coplanar configuration. So we're going to need to rotate this molecule to do that. Okay. Now that we have this anti-coplanar configuration, let's look at our other substituents. So if you notice, we have our ethyl group and phenyl group pretty much on top of on the same side of the molecule, essentially. So we're going to want to draw that when we draw our final product. So what that means is our final product is going to look something like that, because this ethyl group here and phenyl group are on the same side of the molecule, as you can see in the Newman projection. So that's kind of one way to look at it. Another thing you could do is, which I've always found a little bit more confusing, is I'm going to come over here. So drawing out the rotation kind of manually, so you can first rotate. I'm going to draw on your proton, and you can rotate these guys so that you get something like that. And then finally, rotate the other side of the molecule. Sorry, this is getting a little messy. Come down here. So you rotate it again. I'm sorry. Okay, I drew that guy wrong. Okay, and then you can rotate it again. To get something like that. So now essentially what you've got the bromine and hydrogen in the same plane. And so that's kind of another way to do it. And you can see that this guy and this guy are both on the same side of the molecule, which would give you the exact same product. But I find that a little bit confusing, but I guess it's just a matter of preference. Also, later question, I'll show you kind of how to model this with the molecular modeling kit. I think that can be a really helpful way of looking at these elimination processes as well. So this is going to be your final product. Okay, let's look at E. So in this case, we've got, again, a secondary substrate, and we're treating it with the same reagents, sodium methoxide, strong base, strong nucleophile, and we're also using ethanol, which is a polar protic solvent. So we know that this is going to undergo an E2 reaction, but what product will we get? Well, we look at our beta protons. We've got 2 beta protons. So in this case, we don't have really the same issue that we had in question in part F, where we only have a single beta proton. In this case, we have 2 beta protons. So it makes it a little bit simpler. And our major product is going to look something like this. You also could get some SN2 product, as with the previous question, and your minor product, minor elimination product, is going to be something like that, cis configuration. Okay, question 4. When treated with strong base, the following cyclic ether product is formed. Propose a mechanism for the following transformation. Okay, this one's kind of a little bit different. And this is another reaction that you'll go over in chapter 13 next semester. So essentially you have this halohydrin. You'll learn how to make these guys in chapter 8, I believe. And you're treating it with a strong base, let's say sodium hydroxide. So sodium hydroxide comes in, deprotonates, giving you something like this. Now, this should look pretty familiar. You have now a strong nucleophile, and you have a good leaving group, the bromine. So what happens is actually, it's called an intramolecular SN2 process, which forms your epoxide product. So this guy's kind of interesting. And again, like I said, you'll learn more about these halohydrins and epoxides in chapter 8. Okay, question 5. Propose a mechanism for the following transformations. Okay. So first, we have something like this. Okay, we're treating it with ethanol in heat. So this is going to be your SN1 E1 type process, because if you look at your reagent, it's not a strong base or strong nucleophile, it's a weak base. But if you look at what you've got here, this should look kind of familiar. You have a allylic, or once you form your cation, you'll have a allylic carbocation, which, as you know, is stabilized by resonance. So what happens is you can draw your resonance structures. If you look here, out of the two resonance structures, the major contributor is actually going to be this guy here. The reason why is because now you have carbocation in a tertiary carbon versus a secondary carbon. So that'll be kind of important when we're looking at the elimination product. But now I'll just draw something like this, and we can put the these guys are getting kind of sloppy. Sorry. So that's how you get those two SN1 products. Now let's look at how you get the E1 product. So again, you start with this guy here. Loss of leaving group. Gives you the carbocation. You could then again, draw the resonance Now, this guy here is going to be your more significant resonance contributor, where you now have your base coming in, doing an E2, or I'm sorry, an E1 type reaction to produce your final product. And again, the reason why your final product is not something like this is because when you draw out these resonance structures, you realize that the more significant contributor will be the one in which you have that positive charge on the tertiary carbon center, and that's where the proton will be extracted and the double bond will form, which is why you get a final product like this and not like that. Okay, question 6. When 2-bromo, 2-methyl hexane is treated with sodium ethoxide and ethanol, the major product is 2-methyl hexene. Draw a mechanism for this process. Okay. So the mechanism is going to look something like this. Draw a sodium counter ion there. So you've got a strong base, strong nucleophile coming in and extracting a proton. You have a loss of leaving group of the bromine, and you form your more stabilized alkene product. And again, this is going to be your major product, the most significant product, because you have the double bond forming in the more substituted position. Now, what is the rate equation for the proposed process? Well, you have a strong base, strong nucleophile. You know that this is going to be an E2. So the rate will be dependent on both the substrate and nucleophile. Okay, what would happen to the rate if the concentration doubled? So if the concentration doubles of base, the rate is going to double. Okay. Now it's asking us to draw out an energy diagram. Let me draw out kind of a generic energy diagram. Here's your energy. Let me draw out the starting material. And then draw the final product. And so it's going to be something like that. Because this is an E2 process, you're only going to have that one transition state. And let's draw out transition state. And then your little double dagger there to denote that as your transition state. Okay, question 7. Identify the tri-substituted pi bond within the following structure and determine whether it has an E or Z configuration. Okay, let me draw out a little cheat sheet for you guys here. Okay, so the only alkene that's tri-substituted is right here. And in this case, what you want to do is look at the substituents and figure out which one is more substituted. So in this case, this guy here and here are the two more substituted substituents that are connected to that alkene. And so the configuration in this case is going to be E. Second part of the question, part B, how many stereoisomers are possible for this compound? So in order to determine that, we need to use this equation here. Oops. Sorry, guys. Come on. 2 to the n, where n equals number of chiral centers plus EZ configuration. So in this case, let's first count out the number of chiral centers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chiral centers. Now we notice that we have 3 alkenes, which would mean that you have 3 different, or you could have several different EZ configurations with those alkenes. And so in this case, we've got 3 G, so it would be 2 to the 13. I'll plug that into my calculator real quick. I get 8,192 possible stereoisomers. Okay. Question 8, predict the product and explain the regiochemical outcome. Okay, so we know that tosyl chloride can turn a poor leaving group, like an alcohol, into a good leaving group. And we know that DBU is a strong base. So what we're doing is we're turning an alcohol into a good leaving group, and then we're performing a elimination type reaction. So when we do elimination reactions, we first need to identify our beta protons. And in this case, we have 2. Okay, now it says predict the regiochemical outcome. So again, like I've mentioned several times, in E2 reactions, you have this kind of tricky stereospecificity. The proton that's being abstracted needs to be anti-coplanar to your leaving group. It has to be. So the key to determining which, or I should say where the alkene will form is in determining what proton is going to have that anti-coplanar configuration. And if in fact both protons have an anti-coplanar configuration, you just might get a combination of both products. But in this case, let's first look at the configuration of those two beta protons to determine what it's going to form. And I'm going to do this two ways. I'm going to show you how to do it on paper, but then I'm also going to show you with my modeling kit how you can kind of look at this problem. So in this case, you notice that this part of the molecule is really irrelevant. So I'm just going to kind of cross that out for simplistic sake. And you'll notice that a lot of the questions in the book use these really complex molecules. And as you progress on through organic chemistry, it seems like the compounds that just keep getting bigger and bigger, and it can be kind of confusing, but it's important to kind of pinpoint the particular part of the molecule that's actually involved in the reaction in order to kind of streamline things and be able to focus on actually what the problem is asking. So first, what I want to do is draw this part of the molecule, ignoring this guy over here, and I want to draw my chair configuration. Okay. I need to draw that. I'm going to draw this guy as OTS, assuming that the tosyl chloride has reacted with the alcohol to produce your phosphate, good leaving group. Okay. So from looking at the chair configuration, you can already see that you have a beta proton that is anti-coplanar, and that would be this guy here. This guy here is not anti-coplanar. This guy here, he's not anti-coplanar. So the reaction cannot occur on that with that proton there. So we know that the double bond is going to form right here, which would give us final product that looks something like that. Again, ignoring the other part of the molecule. So kind of a simple way to go about it, but I'm also going to quickly show you guys how to do this with the molecular modeling kit so that you can practice this at home and really get the concept down. Give me a second here. Okay, so I put together the molecule here again. These two carbons would be connected to that other part of the molecule that I omitted. But let me make it so you guys can see things here. So here is your leaving group. This would be the tosylate, okay? And this red ball here simply is the CO2CH3 group that you see at the bottom, abbreviated. And you'll notice that if you're looking at these, at your leaving group, and you're looking at the two protons, the two beta protons, which are, let me see here, here's one of your beta protons, and here's your other beta proton. Now, if you're looking from this direction here, you'll notice that this proton is anti-coplanar to your leaving group. Okay, now if you look from the other direction, you're now looking at your leaving group here, you notice that the ethyl group and the proton, the ethyl group is actually anti-coplanar to your leaving group, but the proton is not. And because of the ring structure, there's really nothing you can do, no matter what configuration you try to put this guy in. You're never going to get this proton here into an anti-coplanar configuration with your leaving group right here. And so you'll notice that the only proton, the only beta proton that could be abstracted would be this guy here. Okay, so again, that's kind of an easy way to go about looking at this problem. If you have a molecular modeling kit, I suggest practicing using it and putting together molecules, and then you can practice some of these E2 type reactions with the modeling kit and determine the regiochemistry that that will occur when you're undergoing that elimination reaction. So definitely suggest practicing with the modeling kit if you have that available to you. Okay, question 9. This reaction is stereoselective and produces predominantly the trans-stilbene product. Explain. Okay, so you have a secondary substrate, okay, and you have a strong base, strong nucleophile. You know that you're doing the elimination E2 reaction, and the question is, why is the trans product the major product? We already learned a little bit about or talked about, I should say, how the trans configurations can be more stable because of steric effects. So in order to analyze this, what I'm going to do is draw out my Newman projection. And so we've got two abstractable protons here. So what I'm going to do is draw two Newman projections that have both abstractable protons in the anti-coplanar configuration. And then we can analyze the other substituents that are connected to that carbon center. And I'm denoting the phenyl group with just a PH. So it's just an abbreviation. You'll see that a lot. Okay, so you notice in both cases, prior to the elimination reaction from occurring, you have your bromine, essentially your leaving group, in an anti-coplanar configuration with an abstractable proton. You have that in both cases, both the cis and trans. Now, the difference is really when you analyze these substituents. You've got a phenyl group here, right? Oops, that didn't work well. So you've got your phenyl group, and in this case, with the cis configuration, you've got both of these phenyl groups on the same side of the molecule. So that's going to contribute to a fair amount of steric interactions. That's going to make that reaction a little bit more thermodynamically favorable, I guess. But in the case of this reaction, it's not going to be desired because it's going to require more energy for that reaction to occur. So if you look at the trans product, you have the phenyl groups on the opposite side. You have significantly reduced steric interactions, and so that's why the trans product is predominant. So you're looking at these guys here. Okay, question 10. Which of the following is the major product of this reaction? So again, we have a secondary substrate, and we have a strong base, strong nucleophile. So we know that secondary substrate, strong base, strong nucleophile, the elimination reaction is going to predominate. And in this case, we have a non-sterically hindered base. So our major product is going to be the trans alkene. Question 11, which of the following can be used to make 2-butene? So first, let me draw out 2-butene for you guys. Anytime you have a question like this, you should always draw out the structures to really visualize it. Never try to answer the question without drawing it out. So in this case, we've got 2-butene, and so now we're looking at the different possibilities. So in this case, we only have beta protons here. Okay, so you're going to have, when these hydrogens get abstracted, you're going to produce the Hofmann elimination product. So you're not going to get 2-butene. So it's not A. Let's look at B. So here we have concentrated sulfuric acid and heat. So this would be an E1 mechanism, right? And so you're going to have the alcohol is going to get protonated, which is going to form an oxonium ion, which is now a good leaving group. And you then can have, let me see, draw out your beta protons. And again, in this case, I should say, you'll get this product. So this will produce your trans butene. And let me see here, tosyl chloride and pyridine. Again, this guy, for C, this is going to produce your Hofmann product. Okay. It's not going to be C. And then let's look at D. We've got a good leaving group, and we've got a strong base, strong nucleophile. And again, this guy is going to produce something like that. So now we kind of have a tie here. I'm sorry. In this case, this guy is going to do mostly your E2 or SN2. So answer is going to be B. Okay, last question. There are 2 stereoisomers of 1,2-tertbutyl 4-chlorocyclohexane. One of these isomers reacts with sodium ethoxide in an E2 reaction that is 500 times faster than the reaction of the other isomer. Identify the isomer that reacts faster and explain the difference in rate for these 2 isomers. Okay, so first I'm going to draw 1-tertbutyl 4-chlorocyclohexane. Okay, now, oops, sorry, let me draw this guy a little different. So here's your 2 isomers. I'm drawing these guys gigantic for some reason. Okay. So here's your two isomers, and the question is which one will react faster? Now, you notice the tert-butyl group is locked in that the same position on both molecules, and you're probably wondering why. Why didn't we draw a dash on one of those? And the reason why is because tert-butyl, when we draw out our chair configuration, tert-butyl is going to be very unstable in the axial position. So it's going to occupy only an equatorial position because of the steric interactions. Okay, so in both cases, we're going to have the tert-butyl group in the exact same spot. But, sorry, these guys are hard to draw. Okay, so we have the tert-butyl group in the same spot. Question is, where's our chlorine? And now in one case we have chlorine here, and then let me draw in our beta protons. What am I doing here? Okay. Okay, now the question is, which chlorine has a proton that is anti-coplanar to it? Okay, now if you look at the bottom molecule here, you have your chlorine in the equatorial position, and there are no protons that are anti-coplanar to it. There just aren't. If you look around, there's none that are anti-coplanar. Okay, whereas if you look at the top molecule here, this guy is anti-coplanar to that guy. Okay, so the isomer that is going to react 500 times faster is going to be this guy here, because you have the chlorine in the axial position, and you have which allows you to have a proton in an anti-coplanar position from that chlorine leaving group. So this guy here will react 500 times faster. Okay, so that's all the practice problems I had for you. This is kind of a quick little overview of some of the reagents that are covered in Chapter 7. So I thought that'd be a good review. But I hope this helps. I hope that everyone does well on their exams. I hope everyone's staying safe. And I will see you guys next time. Thank you.